Hello everyone, welcome to the channel Statistica Hub. So in previous lecture we have studied symmetric and skew symmetric matrices. Okay, my matrix A is said to be symmetric if I have A transpose equals to A, and a matrix A is said to be skew symmetric if we have A transpose equals to minus of A. Okay, now let's look at the orthogonal matrices. Orthogonal matrices. For a matrix to be orthogonal, let's say I have a matrix A, which is a square matrix of order n, n cross n. And this matrix is said to be orthogonal if we have A transpose A equals to A transpose is equals to identity. Okay, and from this we can easily see that A transpose is equals to A inverse. Okay, now I have to check it that whether it possesses inverse or not. Then you can see it like this, that A transpose A is equals to identity, and if we take a determinant on both sides of this, we will get determinant of A transpose, determinant of A is equals to determinant of identity, and we know that determinant of identity is equals to 1 and determinant of A transpose is equals to determinant of A. So by using these properties of determinant, we got that we can write it as determinant of A square, that is equals to 1, and from this we got that determinant of A is equals to plus minus 1. Okay, so the determinant of an orthogonal matrix will be plus minus 1, and so from this we got that A is non-singular as it possesses as it has the value of the determinant which is non-zero. Okay, so A is non-singular, hence A is invertible. Orthogonal matrices are invertible. Okay, and if you look to the properties of these orthogonal matrices, then the corresponding properties of these orthogonal matrices are that if I have two matrices A and B, those are orthogonal. So what does it mean that I have two more A and B as orthogonal? It means that A transpose A is equals to A transpose is equals to identity. Similarly for B, that B transpose B is equals to B transpose is equals to identity. Okay, now if I have a corresponding multiplication of these two matrices AB, it is also orthogonal. Okay, we can check this like that for this to be orthogonal, we should have AB transpose AB is equals to identity. Okay, we can check it like I can write this as B transpose A transpose into A B, which is equals to, okay, which has to be equals to identity. Okay, now A transpose A, I know that as A and B are orthogonal, that A transpose is equals to identity, so this will be written as B transpose identity B, and we know that if we multiply any matrix by identity, this will give us the matrix only. Okay, that is B transpose B. I can write it as B transpose B, and it is as B is orthogonal, then B transpose B is equals to identity, so this is equals to identity. So we got A B transpose AB is equals to identity. So my corresponding multiplication of these two orthogonal matrices is also orthogonal matrix. Okay, and the sum of two orthogonal matrices does not follow are not orthogonal matrices. You can also check it like this, that A plus B is transpose A plus B, that is equals to A transpose plus B transpose and A plus B. Okay, and which is A transpose A plus A transpose B plus B transpose A plus B transpose B. We know that B transpose B is equals to identity as B is orthogonal, and A transpose A is equals to identity as A is orthogonal, but we didn't know anything about this, so it is not equals to identity. So A plus B, the corresponding sum of these two matrices does not follow, are not orthogonal matrix. Okay, and the inverse of an orthogonal matrix is orthogonal. Okay, and the transpose of the orthogonal matrix are also orthogonal. And similarly, if we take a power of this, let's say A's power n, and this also follows orthogonal. You can check these by applying the same rule, which is A transpose equals to A transpose equals to identity. Okay, now to check orthogonality, to check orthogonality. So okay, let's say if I have a matrix which is given as we know that for orthogonal it should follow A transpose equals to identity. Okay, let's say if I have a matrix which is given as A1 B1 C1 A2 B2 C2 A3 B3 C3. Okay, and let's just consider that this is my u1 vector, this is my u2 vector, and this is my u3 vector. Okay, then ui dot uj is equals to 0 whenever if I have I not equals to j, and that will be equals to 1 if I is equals to j, and where uj is equals to delta ij, which is said to be the Kroneker's delta. Okay, what am I doing here actually is that we know that the corresponding dot product of u dot v is equals to 0. If the dot product is 0, then we say that u and v are perpendicular to each other, or they are orthogonal. Okay, we have studied this in the dot product case. Okay, the same case is applying here, that I have these three vectors which are u1 u2 u3. If the corresponding multiplication, if the corresponding dot product of these vectors is equals to 0, okay, for I not equals to j. Okay, and for other cases, that for I is equals to j, for let's say u1 dot u1, and similarly u2 dot u2 and u3 dot u3, if for these we have the value equals to 0, sorry, equals to 1, then for by this we say that by this we can check that whether a matrix is an orthogonal or not by the dot product property. Okay. Okay, now there is a matrix which is said to be which is no, sorry, normal matrices. Okay, normal matrices. So what are normal matrices is a real matrix A. A real matrix A is said to be normal if it commutes with its transpose. Okay, normal if it commutes with its transpose. Transpose, that is, I means to say that A transpose A equals to A transpose. That's when we say that my matrix is normal. Okay, and you can see that symmetric, orthogonal, and skew symmetrics. Okay, these all are, if my A is symmetric, orthogonal, and skew symmetric, then A is my normal. Okay. Okay, now we have seen these matrices that are symmetric, skew symmetric, uh, orthogonal, and normal. Okay, so these matrices we have studied on our real field. Okay, real field. So these are the matrices which are dependent on the real field. And now if we look to the complex field, okay, now these corresponding matrices are said to be Hermitian, skew Hermitian, skew Hermitian. Orthogonal is unitary in the complex field, and normal is normal in the complex field. Okay, so in the complex field, in the real field, they are named as symmetric, skew symmetric, orthogonal, and normal, and in the complex field they are named as Hermitian, skew Hermitian, unitary, and normal. Okay, and normal is stay normal. Okay, the names of these matrices have changed. So technically they are the same matrices, but on the different fields. Okay, so now let's just talk about the complex matrices. Complex matrices. Okay, so let's say if I have this matrix A, and which is defined as Aij. Okay, and it has complex entries. With complex entries, those are like z is equals to a plus ib. Okay, this is my complex entry of this matrix A. Now we can take a conjugate of this z, which is defined as z conjugate is equals to a minus ib. This is said to be the conjugate. Okay, and a conjugate is equals to aij conjugate. This is said to be the complex conjugate, complex conjugate of matrix A. Okay, and we can find the modulus of this z by mod of z equals to root of a square plus b square. Okay, now there are some properties of these complex matrices, that those are like that A is matrix there, when A is my matrix, then A's conjugate is equals to A. Second property is that A plus B, the corresponding sum of these two matrices conjugate is equals to A's conjugate plus B's conjugate. And third is AB's conjugate is equals to A conjugate into B conjugate. And fourth property is A conjugate transpose equals to A transpose conjugate. Okay. And fifth is Ka, where K is a scalar, Ka scalar's conjugate is K conjugate into A conjugate. Okay. Now we have defined this, that A transpose conjugate. A transpose conjugate is said to be the A theta. This is said to be the conjugate transpose of a matrix. This is conjugate transpose of a matrix. Okay, the conjugate transpose of a matrix is defined by A's power theta. Okay, and it also follows some properties, that is conjugate transpose of a matrix, that is A's power theta is equals to A. Second is A plus B's whole theta is equals to A's theta plus B's theta. These are the properties of conjugate transpose of a matrix. Okay, and K A's theta is equals to K conjugate into A's power theta. And similarly, fourth property is A B's theta complex conjugate of a matrix is B theta into A's power theta. Okay, and another is that I have a matrix A which is non-singular. Non-singular means it possesses an inverse, then A theta's inverse is equals to A inverse theta. Okay, and this A inverse theta is the inverse of A theta. You can see that. Okay, that it is the inverse of A theta. Okay, now let's just see unitary matrices. Unitary matrices. So we have unitary matrices which are defined as A thetas into A is equals to A into A theta is equals to identity. Okay, so this is my corresponding unitary matrices. That's how we define it, and we have say that we define orthogonal like that A transpose A equals to A transpose A equals to identity. So in the complex matrices, we have just replaced A transpose by A theta, and this is the corresponding condition for the unitary matrices. Okay, so you can see that A inverses is equals to A theta here. Okay, by applying like this, you can say it like this. And unitary matrix you can is like, let's say 1 plus I by 2, 1 minus I by 2, and 1 minus I by 2, 1 plus I by 2. Okay, this is that. How can you see that this is a corresponding unitary matrices? Okay, unitary matrix. And every real unitary matrix is a real orthogonal matrix. What we are saying, that every real unitary matrix is real orthogonal matrix, because we know that these are the same matrices but on the different fields. These are the same properties of the matrices but on the different fields. One is on for the complex and one is for the real. Okay, real orthogonal matrix. Okay, so we have defined A theta A is equals to identity. So let's just take a determinant of this. That will be A determinant of A theta, determinant of A is equals to determinant of identity, that will equals to 1. And from this we got that A theta is defined as A transpose conjugate, and we know that determinant of A transpose equals to determinant of A. So we can write this as determinant of A conjugate into determinant of A, and that will be equals to 1. Okay, so this will hold only if I have determinant of A is equals to 1. This condition will hold if determinant of A is equals to 1. Thus, we can say that determinant of unitary matrix A is of unit modulus, and hence A is non-singular and invertible. Okay, so what we are saying is that determinant of unitary matrix is of unit modulus, and as it has determinant of unit modulus, it is invertible. Okay, and you can check it that if I have A and B, which are my unitary matrix, then the corresponding multiplication of these, like AB and BA, are also unitary matrices. Okay, you can check it like that. AB theta is equals into AB has to be equals to identity. Okay, just like we have done in the orthogonal case, you can also check it here for the unitary matrices. Okay, now for any to check unitary unitary, that I have a matrix A which is, let's say, A, B, C, and A transpose, B transpose, C transpose. We can check it like this, that the corresponding, let's just say this is my U vector and this is my V vector. Then if the corresponding dot product of this U dot V is equals to 0, then we say that it is uh, orthogonal. Okay, if these are orthogonal, and if the corresponding dot product of U dot U and V dot V is equals to 1, then these are the corresponding equations, that U dot V is equals to 0, and if dot U and V dot V is equals to 1. So then can we say that this is the corresponding unitary matrix, and you can see that these are the same properties for the orthogonal matrices too. Okay, that the corresponding dot product matrices. So for this we can say that that mod of A square plus mod of B square plus mod of C square has to be equals to 1, and A dot A transpose conjugate plus B transpose conjugate plus C transpose conjugate is equals to 0. Okay, so then can we say that these are my corresponding unitary matrices for checking unitary matrices. Okay, so let's just see now Hermitian and skew Hermitian matrix. Hermitian matrix are defined as when I have a matrix which is as Aij, and it is said to be Hermitian if A theta is equals to A. Okay, that is, we mean to say that Aij is equals to Aji's conjugate. Okay, and from here we can just expand it like A transpose conjugate is equals to A and A conjugate equals to A transpose. Okay, that's what we have got, that A's conjugate is my A's transpose in the Hermitian case. So for diagonal elements, if we look to the diagonal elements, then for diagonal elements we have AII is equals to AII conjugate by applying this. Okay, AII is equals to AII conjugate, and so from this we can see that every diagonal element of Hermitian matrix is real. Okay, because that will be the only possible case when AII is equals to its conjugate. Okay, so every diagonal element of Hermitian matrix is real. Okay, now let's just see skew Hermitian. Skew Hermitian. A matrix A, which is Aij, is said to be skew Hermitian if we have A theta equals to minus A, that is corresponding element as Aij equals to minus of Aji's conjugate. Okay, and you can see it like Aij plus Aji conjugate is equals to 0, and we have Aij, let's say, which is A plus IB. Then if we'll take a corresponding conjugate of this Aij, that will be equals to A minus IB. Okay, by putting these value, we got A plus IB plus A minus IB. That will be equals to 0. So that will be this cut out, and we got A is equals to 0. So we got that Aij is equals to IB. Okay, so if we'll talk about the diagonal elements of skew Hermitian must be either a pure imaginary number or must be 0. Okay, so the diagonal elements of skew Hermitian must be either a pure imaginary number or 0. Okay, okay, now if I have a matrix A which is my complex square matrix, now I can represent this matrix A like A is equals to A plus A theta by 2 plus A minus A theta by 2. because if I just normally calculate this, that will be equals to A. And this is my matrix P, and this is my matrix Q, let's say. And this matrix A is said to be Hermitian, and this matrix Q is said to be skew Hermitian. Okay, so that's how we can represent a matrix A, which is of complex square matrix, into the two parts, which is Hermitian and skew Hermitian matrix. Similarly, we can represent for the uh, real field also, real square matrix also, into the symmetric and skew symmetric matrices. Okay, now let's see normal equation in complex field. No, sorry, normal matrix in complex field. The normal matrix in complex field are said to be that commutes with A theta. Okay, a matrix A with commutes with complex conjugate of the matrix A. That is A theta equals to A theta A. This is said to be the normal matrix in complex matrix. Normal matrix in complex field. Okay. Now there are some more matrices which are idempotent matrices. Idempotent matrix. A matrix A is said to be idempotent if we have A square is equals to A. Okay, if we have A square is equals to A. Okay, now if we take a determinant of this, that mod of determinant of A square is equals to determinant of A, and that be equals to determinant of A square minus determinant of A, which is equals to 0, and taking out determinant of A, we got determinant of A minus 1 is equals to 0, and we got determinant of A is either 0 or 1. Determinant of A is equals to 0 or 1. Okay, now what are actually idempotent matrices are that we have, let's say, identity matrix 1 0 0 1. This is my corresponding identity matrix, and which is equals to A. Okay, and if we take if we multiply the identity matrix into itself, that is A square equals to, and that will be equals to identity. Okay, that gives us A square equals to A. Okay, now every non-singular idempotent matrix is actually identity matrix. What we are saying that every non-singular idempotent matrix is identity matrix. Okay, so why are we saying this? We are saying every non-singular idempotent, every non-singular means that a determinant of A is not equals to 0. That's when we say that it is invertible. So when determinant of A is not equals to 0, it means that my matrix A is invertible. Okay, so for idempotent we have A square is equals to A. That means A into A is equals to A, and by multiplying A inverse both sides, that is A inverse A into A equals to A inverse into A, we got that V equals to identity. A inverse into A is equals to identity, and A inverse equals to that V also equals to identity. We have A is equals to identity. Okay, and then can we say that? Then we can say that every non-singular idempotent matrix is identity matrix. Okay, now we have two identity matrix, idempotent matrices, that are A and B. These are my corresponding idempotent matrix. Okay, then AB, that is the multiplication of these two matrices, are idempotent if this will be idempotent if A and B commute. Okay, so you can check it like we have done previously. So AB, the matrix multiplication of these idempotent matrices will be idempotent if A and B commute. Okay, now let's see nilpotent matrix. Nilpotent matrix. Okay, we have nilpotent matrix when A's power m is equals to 0 for m belongs to the natural number m, where m is my least positive integer. And A is said to be here nilpotent matrix of index m. Okay, so these are those matrix A's power m is equals to 0. We means to hear this, that at what power of A it became the 0 matrix. Okay, so a nilpotent matrix of index m that at power m, when we have done a's power m, when we multiply a m times, then we got a's power m is equals to 0. So this is said to be the nilpotent matrix. Okay. Now we have another matrix which is said to be involuntary matrix. Involuntary matrix. These are those matrices which are a square is equals to identity. Okay, and we can write this as I minus a square is equals to 0. That is I minus a, I plus a is equals to 0. Okay, now in identity matrix is all involuntary. You can see it like that a is equals to identity I got, and a is equals to minus of identity. Okay, now if we take a determinant of this, that determinant of a square is equals to determinant of identity, then we can see that determinant of a is equals to plus minus 1. So for involuntary matrix, the determinant of a is plus minus 1. So and it is invertible. From this we can see that it is invertible. Okay, now let's just see that we have talked about involuntary in idempotent matrix, involuntary matrix. Okay, now these matrix are, if we talk about the idempotent case, then my for idempotent we have a square equals to a. Okay, so the if you look at like this, that if I have a matrix a which is let's say 1 1 1, okay, and the other elements here which are 0, then it satisfies the property of a square equals to a. It will satisfy this property. Okay, if I have this first row which is 1 1 1, and other than these elements are 0 0 0 0 0, all are 0, then it will follow the property of idempotent. Okay, similarly, let's say I have this matrix where the diagonal elements is either 0 or 1. Okay, where these diagonal elements are either 0 or 1 and all the other elements are 0, then it will also follow the satisfy the property of idempotent matrix, that it is equals to a. If we have matrix something like these, then we can just check it by normal calculating that they follow the idempotent property. Okay, similarly for involuntary matrix, that we have involuntary matrix when we have a square is equals to identity, and we got from here that you can see that an identity matrix is involuntary. Okay, okay, now let's see a question which is say that if I have a matrix a and that is my skew symmetric matrix. Okay, so if it is a skew symmetric matrix, then I got this information that A transpose equals to minus of A, and I have asked this that if A is a skew symmetric matrix, then A's power 2020 is skew symmetric or not. I have to check this. Is skew symmetric or not? Okay, now if I have A which is my skew symmetric, A transpose equals to minus of A. Okay, now let's just take A n's transpose, and we know that that will be equals to A transpose n. My A's power n transpose is equals to A transpose power n. Okay, now we have to check for this, that if A is skew symmetric, then minus of A's power n, what will be that? That is equals to minus of 1 minus 1's power n into A. Okay, so from this we can make the case that if my n is even, that will be symmetric, because it will be equals to A. Okay, this minus 1 term will vanish if my n is even. Okay, if n is odd, then this matrix will be uh, skew symmetric, because in this case I have this A transpose is equals to minus of A, and we have here an where my n is 2020, n is equals to 2020, and you can see that this n is even. So my corresponding matrix which is A's power 2020, by applying these property is even, so it is symmetric matrix, not skew symmetric. A's power 2020 is symmetric matrix. not skew symmetric. Okay, so by applying this property of symmetricity, skew symmetricity, you can just solve these problems very easily. Okay, so that's all about this video. Thank you.